Okay, let us start the lecture. So we have done 3 units. Now this is the last unit of this course. So in this unit we discuss Ray's theorem. Okay, Ray's theorem. Ray's theorem. So you can see this from the book Fundamental Theory of Semigroups at page number 69. Okay, page number 69. Okay, we discussed this Ray's theorem here. So first of all, we will try to define the natural order among the idempotents in any semigroup. Suppose आपके पास given semigroup है, you can define partial order on that semigroup. But if you take the idempotent set of the idempotents of that semigroup, then there is a natural order on that. We apply the properties of idempotents. We will see that there is always a natural order on any semigroup among the idempotents. Okay. So like we have a set of natural numbers, so we have a natural order there, that 1 less or equal to 2 less or equal to 3 and so on and so forth. And in a similar way, if we have an idempotent, we have band, if semigroup is consisting of only idempotent, then we have always a natural order on that. तो हम क्या करते हैं, हम कोई सेमी ग्रुप लेते हैं, हम उस पर कोई हम कहते हैं कि ये ऑर्डर हम इस पर लेते हैं, लेस और इक्वल टू ऑर्डर. ओके, सो वी डोंट नो व्हाट इज दिस ऑर्डर एक्चुअली, but in certain semigroups we have always a natural order, like we have a semigroup of natural numbers or we have a semigroup of real numbers. There is always a natural order. So likewise we have a natural order among the idempotents of a given semigroup. Okay, so let S be a semigroup. Let S be a semigroup. And E of S denotes the set of all idempotents of S. Set of all idempotents of S. E of S may be empty. Okay, this E of S may be empty. It may be empty. Now let's try to define this set. In case it is empty, we don't need to define order on this set, but so we assume that here it's non-empty. So define the order less or equal on E of S by, we say E is less or equal to F. So always we will denote idempotent is by E, F, and these notations are natural. So these are standard notations for idempotents, E, F, G. Okay, so we say E and F, they are idempotents of F, they are in E, S. So we say they are related to each other if and only if E, F is equal to F, E is equal to E. So that's a natural. So we'll see that this is actually an order on ES. We show that this one is an order on ES. So first of all, we have to see that it's reflexive. So for any E, for any idempotent E in S, we have to show that E is less or equal to E. So for this, we need to show that EE is equal to EE is equal to E. So let's take let E be in ES. It's an idempotent. Then by definition of idempotent, its square must be equal to E itself. So therefore EE is equal to, say, EE. So we can commute these two things and both are equal to E. So we have this E is less or equal to E, and hence this relation is reflexive. This is reflexive. So next we see that it's also antisymmetric. So for this, let's take two elements. E and F in E of S, such that E less or equal to F and F less or equal to E. Okay. Then by definition of order, it means that EF is equal to FE is equal to E, and here FE is equal to EF is equal to F. So therefore E is equal to F. Therefore E is equal to F. So which implies that the order, this relation is antisymmetric. It's antisymmetric. So finally we see that it's also transitive. So for this we take three elements. So let's take three elements. Let E, F, G belongs to ES, such that E is less or equal to F. Okay, so such that E less or equal to F and F less or equal to G. So this gives EF is equal to FE is equal to E, and FG is equal to GF is equal to F. So we need to see that E is related to G. So that means we have to show that EG is equal to GE is equal to E. So now let us start with EG. Now EG. So substitute the value of E here. It's either EF or FE. EF or FE. So what will be suitable? I should write FG because I should write E is equal to EF so that I can apply this FG. Okay. I can apply FG. So it's equal to E is equal to EF. EFG. Then you can apply the associative law. You can write it as E times FG, but that one it's equal to F. It's equal to EF. Now again EF it's equal to E. And let's see G. ये भी E के बराबर नहीं आना चाहिए G. So GE, अब यहाँ पर मैं F का वैल्यू क्या लूँ, FE लूँ या EF? So I should take FE because then I can apply GF here. Okay, so it's G, then value of E. It has two values, so I take this value FE, then I can apply the value of GF from this equation. It's equal to F, so it's FE is equal to E. So EG is equal to G, so therefore EG is equal to GE is equal to E, so which implies that E is related to G is less or equal to G. And so this relation is transitive. So So the relation less or equal to is transitive, and hence this is an equivalence relation. Equivalence relation. So that we have already discussed that this, yes.
So it defines an order, not an equivalence.
Okay, sorry. So it's an order. It's an order relation. Okay. Okay. Thank you. So this is an order relation. तो जैसे मैंने पहले बताया था आपको कि ये जो है ना सेट ऑफ आइडेम्पोटेंट्स, इट मे बी एम्प्टी है, दिस सेट मे बी एम्प्टी. In general, it's not non-empty. So like we have a semigroup of even natural numbers. Under multiplication, you can take that is semigroup, but that does not possess any idempotent. Okay. So but finite semigroups always possess idempotent, because the order of finite semigroup, order of every element of finite semigroup is finite. And we have done that finite monogenic semigroup, इसका एक वो सब ग्रुप एग्जिस्ट होता है, तो that subgroup has an identity, and that identity is the idempotent of that finite semigroup. So finite semigroups always possess idempotents, okay, but infinite in general may not. So take an example of this set of natural numbers under multiplication. You can take that does not possess any idempotent. However, if we have a semigroup with 0, अगर आपके पास semigroup होगा, 0 semigroup होगा आपके पास, then 0 is always idempotent, because 0 square is equal to 0. But we are not interested in 0, so we take we are interested in the non-zero idempotents actually. So suppose we have a semigroup having non-zero idempotents, then we want to find the minimal idempotent. Minimal idempotent may be more than one. That you have already seen that minimal element, if exist, it may exist more than one. It may there may be two or more than two minimal elements, but minimum is unique always. So if we have non-zero idempotents, then there is this set of non-zero idempotents, we have a natural order on that set of idempotents. So then this set either may possess the minimal element or not. In case 0 is idempotent, then 0 is always minimal element, so that's always true. But non-zero minimal idempotent, it may or may not possess. So in case we have a non-zero minimal idempotent, suppose अगर होगा किसी सेमी ग्रुप के पास आइडेम्पोटेंट्स का सेट आपके पास आ जाएगा, उसका नॉन-जीरो मिनिमल आइडेम्पोटेंट होगा, उस आइडेम्पोटेंट को हम कहते हैं प्रिमिटिव आइडेम्पोटेंट. नॉन-जीरो मिनिमल आइडेम्पोटेंट इज कॉल्ड ए प्रिमिटिव आइडेम्पोटेंट. और अगर सेमी ग्रुप के पास प्रिमिटिव आइडेम्पोटेंट हो, जीरो सेमी ग्रुप के पास अगर प्रिमिटिव आइडेम्पोटेंट हो, उस सेमी ग्रुप को हम कहते हैं कंप्लीटली जीरो सेमी ग्रुप. ओके, सो लेट्स राइट दिस. if S is a semigroup with 0, if S is a semigroup with 0, if S is a semigroup with 0, okay, then the defining properties of 0, जो 0 की जो properties है, it is a minimal idempotent among all the idempotents. Then by defining properties means that 0 into 0 is equal to 0, 0 into any element is equal to 0, and by defining properties of 0, defining जो इसकी definition है 0 के element, क्योंकि by defining properties of 0 की जो प्रॉपर्टीज डिफाइनिंग प्रॉपर्टीज मतलब जो इसकी डेफिनेशन है डिफाइनिंग प्रॉपर्टीज ऑफ जीरो एलिमेंट defining properties of zero element it immediately follows that you can also verify it, okay, it immediately follows that zero is the unique minimal idempotent. Zero, okay, let's write it in words. Zero is the unique minimal idempotent, okay, among idempotent you are taking this minimal element among idempotents because the natural order is defined on idempotents only, okay. So the idempotents that are minimal, अब वो आइडेम्पोटेंट्स जो मिनिमल होगी विद इन द सेट ऑफ नॉन जीरो आइडेम्पोटेंट्स, मतलब वो ऑब्वियसली नॉन जीरो ही होगा, वो आइडेम्पोटेंट जो मिनिमल वो नॉन जीरो होगा, द आइडेम्पोटेंट्स, और वो एक से ज़्यादा भी हो सकते हैं, दैट्स व्हाई इज यूजिंग दिस आइडेम्पोटेंट्स, ओके। अगर मिनिमम होता तो उसकी इसमें यूनिक, ओके। द आइडेम्पोटेंट्स दैट आर मिनिमल, दैट आर minimal within the set of all non-zero idempotents, within the set of all non-zero idempotents are called primitive, इनको हम कहते हैं primitive, और कॉल्ड, जैसे आपने प्रिमिटिव एलिमेंट्स में नंबर 3 में भी डिफाइन किया होगा प्रिमिटिव, तो यहाँ पर भी इस आइडेम्पोटेंट, किस आइडेम्पोटेंट को हम प्रिमिटिव कहेंगे। सो दस इफ, सो देयरफॉर इफ इज प्रिमिटिव आइडेम्पोटेंट, इफ इज primitive, so that means it's minimal, okay, primitive, then for any idempotent f, then for any non-zero idempotent, okay, any, so that means this is there is no any idempotent f which precedes e, okay, so then for any non-zero idempotent f with f is related to e implies that this f should be equal to e, तो कोई भी there is no any idempotent f which precedes e, अगर कोई ऐसा होगा then that should be equal to e, so that is for any non-zero idempotent f, we have fe is equal to ef, fe is equal to ef is equal to f, this implies that f is equal to e, क्योंकि इसका मतलब यह है कि इसका मतलब क्या है, इसका मतलब यह है कि f less or equal to, वही तो आपने लिखा ना, if f is any idempotent such that f is less or equal to e then f should be equal to e, अब if f less or equal to e को आपने ऐसे लिखा, आपने इसकी डेफिनेशन अप्लाई की है जो इस ऑर्डर की डेफिनेशन है। सो दैट एफ, तो प्रिमिटिव आइडेम्पोटेंट की यही प्रॉपर्टी, अगर ई प्रिमिटिव आइडेम्पोटेंट होगा देन फॉर एनी नॉन जीरो आइडेम्पोटेंट एफ, इफ एफ ही, सो वी हैव दिस, if f is equal to ef is equal to f, then this will hold this. Now we define a completely zero simple semigroup. Completely zero simple semigroup. completely zero simple semigroup. जीरो सिंपल मतलब यह है कि जिसके दो ही आइडियल्स हो, जीरो और एस होल एस. ओके, कंप्लीटली जीरो सिंपल सेमीग्रुप. अब कंप्लीटली यहाँ पर टर्म यूज इसने की है. ए सेमीग्रुप विल बी कॉल्ड कंप्लीटली जीरो सिंपल. A semigroup will be called completely zero simple. Okay, will be called complete if it is zero simple first. If it is zero simple, okay, and has primitive idempotent, and has primitive idempotent, and has primitive idempotent. So now in the next step we will see that every finite zero simple semigroup is completely zero simple. मतलब जो भी finite zero simple semigroup होगा, finite zero simple semigroup का मतलब क्या है? ये zero semigroup होगा और इसके पास दो ही ideals होंगे, zero and s itself, और ये finite है. Then it must possess minimal idempotent, minimal non-zero idempotent. Then it must has a primitive element. So that's this proposition. Every finite zero simple semigroup, every finite zero simple semigroup is completely zero simple. Is completely zero simple. तो ये तो है ही है. तो this thing. But interesting question is this: does there exist any infinite? वही actually रीज ने किया है. रीज ने actually infinite completely zero simple semigroup कंस्ट्रक्ट किया. In fact, एक तो इसने इसकी कंस्ट्रक्शन की, वो किस टाइप का होगा, ठीक है, वो किस टाइप का होगा, मतलब एक सेमीग्रुप इसने कंस्ट्रक्ट किया जो कि कंप्लीटली जीरो सिंपल है और इन्फिनाइट है. और फिर इसने ये भी प्रूव किया जो भी कंप्लीटली जीरो सिंपल सेमीग्रुप होगा वो इसी टाइप का होगा जो उसने कंस्ट्रक्ट किया रीज ने. Okay, let's first prove this finite. Okay, finite zero simple semigroup is always completely zero simple. So let S be a finite zero simple semigroup. Let S be a finite zero simple semigroup. So it's finite. So finite means that order of every element of S is finite. So whenever order of every element of S is finite, then for every element A of S there is a power, there is some natural number n such that A power n is idempotent. जो आपने किया जहाँ पर हमने finite monogenic semigroups को डिस्कस किया. फाइनाइट मोनोजेनिक सेमीग्रुप का मतलब कि इट्स लाइक फाइनाइट साइक्लिक ग्रुप. ओके, तो अब आपके पास फाइनाइट सेमीग्रुप है. अब इसमें कोई भी एलिमेंट लीजिए, ऑब्वियसली इसका ऑर्डर फाइनाइट होगा. आप इसके पावर्स लीजिए ना, सो इट विल ऑलवेज टर्मिनेट बिकॉज योर सेमीग्रुप इज फाइनाइट. सो जब ये टर्मिनेट होगा इट मीन्स दैट it means that the semigroup generated by that element is monogenic semigroup. और अगर वो monogenic semigroup होगा, वो अगर suppose A से generate होगा, then you can construct Ka, the cyclic group. उसकी आइडेंटिटी होगी और वो भी क्योंकि वो साइक्लिक होगा, वो आइडेंटिटी ए पावर इंटीजर होगी और वो जो आइडेंटिटी उसकी होगी वो इस सेमी ग्रुप का आइडेम्पोटेंट होगा. इसकी आइडेंटिटी तो नहीं हो सकती इन जनरल क्योंकि वो के ए जो है ग्रुप जो है साइक्लिक ग्रुप वो उसकी आइडेंटिटी है और एस तो बिगर देन है के से. सो मेरा कहने का मतलब यह है कि अगर आपके पास जो भी फाइनाइट सेमी ग्रुप होगा उसका जो भी एलिमेंट आप लोगे उस एलिमेंट का कोई पावर एग्जिस्ट होगा जो आइडेम्पोटेंट होगा फाइनाइट के लिए. ओके, ये फाइनाइट का रिजल्ट है. इसमें जीरो सिंपल का मतलब यूज आप नहीं कर रहे हो. So I will write here since S is finite. Since S is finite. क्योंकि अगर मैं डायरेक्ट यहाँ से लिखूंगा कि पावर आइडेम्पोटेंट होगा तो आपको ये कन्फ्यूजन होगा. शायद मैंने दोनों चीज़ें यूज़ की, फाइनाइट एज वेल एज जीरो सिंपल. मैं सिर्फ फाइनाइटनेस की प्रॉपर्टी यूज़ कर रहा हूँ इसमें. S is finite. Since S is finite. Since S is finite. So every element of S has a power which is idempotent. So therefore every element of S has a power which is idempotent, which is idempotent. Right. तो एक्चुअली मुझे क्या करना है, मुझे प्रूव करना है ये कंप्लीटली जीरो सिंपल. कंप्लीटली जीरो सिंपल के लिए सबसे पहले आपके पास नॉन जीरो आइडेम्पोटेंट्स होनी चाहिए. देन यू कैन फाइंड द मिनिमल. ओके, पहले तो होना चाहिए ना कोई नॉन जीरो आइडेम्पोटेंट. जीरो तो है ही आइडेम्पोटेंट, तो अब आपको एक्चुअली नॉन जीरो आइडेम्पोटेंट चाहिए. हम अज्यूम करेंगे सपोज जीरो ही इसका आइडेम्पोटेंट है. जीरो इज द ओनली आइडेम्पोटेंट ऑफ एस एंड वी मस्ट अराइव एट ए कंट्राडिक्शन. तो जब आपको उसमें कंट्राडिक्शन मिल जाएगी सो यू कैन से दैट दिस सेमी ग्रुप मस्ट पोजेस नॉन जीरो आइडेम्पोटेंट्स. So then you will see the minimal element of that non-zero idempotence is actually a primitive element, and hence our semigroup is completely zero simple. Okay, so for if zero is the only idempotent of S, सपोज जीरो सिर्फ एक ही आइडेम्पोटेंट एस का, देन फॉर ऑल एस इन एस, क्योंकि एस का कोई पावर तो आइडेम्पोटेंट होगा ना, देयर एग्जिस्ट एन ग्रेटर इक्वल टू 1 सच दैट एस पावर एन इज इक्वल टू जीरो, क्योंकि जीरो ही सिर्फ एक आइडेम्पोटेंट इसका है और एस का कोई पावर एग्जिस्ट होगा जो आइडेम्पोटेंट होगा, बट इट इज गिवन दैट जीरो इज द ओनली आइडेम्पोटेंट. सो देयर इज सम एन सच दैट एस पावर एन इज इक्वल टू जीरो, व्हिच मीन्स दैट एस पावर एन इज इक्वल टू एस पावर एन प्लस में ये भी आगे जो पावर्स होगी वो सारी जीरो के बराबर होंगे, बिकॉज एस पावर एन इज इक्वल टू एस पावर एन इंटू एस, दैट्स जीरो इंटू एस, विच इज इक्वल टू जीरो. सो दिस थिंग होल्ड, सो विच मीन्स दैट एक्चुअली दिस एस इज एक्चुअली द निलपोटेंट एलिमेंट ऑफ एस. निलपोटेंट एलिमेंट होगा इस एस का. सो इसको आप ऐसे रखिए यहाँ पर, नेम इट 1. Now let's take any non-zero element. Now let A be any non-zero element. A be any non-zero element. Then we know that S is equal to SAS, because SAS is ideal, but it has no any ideal because it is zero simple. So SAS must either equal to 0 or S, but it can't be equal to 0. जो आपने किया proposition, आप मैं यहाँ पर वो proposition ही लिखूँगा by proposition. It's the proposition 3.1.2. you can see that proposition. Okay, so since now since this A is in S, so A must be in SAS. It means that there exists x and y in S such that A is equal to x and y. So let's choose x y in S such that A is equal to x a y. Now again substitute that value of a equal to x a y, it's equal to x square. So मैं इसको complete यहाँ पर लिख दूँगा. So this gives right here this gives okay, this gives a, it's equal to x a y, which is equal to x square a y square, we can write by 1 by 2, okay, limit 2, and this is equal to x cube a y cube, because again a equal to x a y, again by 2. So continuing this is equal to x power say k a y power k for all k greater or equal to 1. But there is some power of x which is idempotent, and that idempotent equal to 0. So this implies that a equal to 0. This implies that a equal to 0 by 1. A is equal to 0 by 1, which is a contradiction because a is non-zero, which is a contradiction, which is a and hence S possesses non-zero idempotence. Hence this S must possess non-zero idempotence. Non-zero, okay, non-zero idempotence. S must possess non-zero idempotence. So now I will show that it among the non-zero idempotents it must have minimal element. So let's write this. Let E of S, not the, we should not write E of S because E of S will denote all the idempotents. It may contain also 0. So let's write this. Let Y be the set of non-zero idempotents of S. Then Y is finite because S is finite. Now अगर suppose आपने इसमें से कोई आइडेंटिफायर चूज किया, let E1 belongs to Y. अगर E1 ही मिनिमल होगा then E1 is primitive, क्योंकि मिनिमल जो भी होगा वही primitive होगा. If E1 is minimal then there is nothing to prove. If E1 is minimal then there is nothing to prove. There is nothing to prove. Okay, there is nothing to prove. So assume E1 is not. So assume E1 is not minimal. E1 is not minimal. So there must exist E2 such that, so thus there exists E2. Thus there exists E2 in Y such that this E2 is less than E1. Okay, E2 is less than E1. Again, if E2 is minimal then there is nothing to prove, and so assume that E2 is not minimal. We can always find E3. So so now if E2 is minimal then there is nothing to prove. If E2 is minimal, then there is nothing to prove. There is nothing to prove. Nothing to prove. So assume E2 is not minimal. Assume E2 is not minimal. Okay, then there exists E3. There exists E3 idempotent in Y such that E3 less than E2 is less than 1. So by continuing this process, if suppose Y does not possess minimal element, if suppose this we can must terminate, okay, because it's finite, Y is finite. So suppose Y does not possess minimal element, suppose Y के पास minimal element नहीं होगा, then there is infinite chain, then there is an infinite chain. आपके पास एक infinite chain आ जाएगी. It's E1. Okay, so which like this: E1 greater than E2, greater than E3, and so on and so forth, which is a contradiction because Y is finite. there is an infinite chair in y, you can say in y, such that this holds, which is a contradiction, which is a contradiction as required. तो कंट्राडिक्शन किसको मिली? आपने एज्यूम किया था कि इसके पास मिनिमल एलिमेंट नहीं है, तो वहाँ से कंट्राडिक्शन आ गई। इसका मतलब है कि इसके पास मिनिमल एलिमेंट है, और वही मिनिमल नॉन जीरो एलिमेंट जो होगा वही इसका क्या है, प्रिमिटिव, एंड हेंस एज रिक्वायर्ड बस। दैट्स द एंड ऑफ दिस थ्योरम। ओके, सो आज हम इसमें इतना ही करेंगे। So in the next lecture we will see that how to construct infinite completely zero simple semigroup.